So with those notes out of the way, I'd like to thank everyone again for joining us in today's webinar, Flee from Parsimony, Escaping the Boundary Condition Paradox in Groundwater Modeling. What is the boundary condition paradox? Well, if you've ever built a groundwater model, you know how important it is to get an accurate estimate of recharge rates to apply as a boundary condition. But an accurate estimate of the effective recharge rate would actually be an extremely valuable model output. In many studies, what we're actually interested in knowing is the sustainable rate of groundwater extraction, which is closely related to the effective recharge rate of an aquifer. So that is the paradox. For most hydrological models, we must apply recharge rate as a fundamental input to the model, although what we really desire is recharge as a model output. Fully integrated hydrologic models like hydrogeosphere don't struggle with this paradox because they rely on a physics-based framework which bridges the gap between groundwater and surface water flow. Discharge or recharge areas are not specified in hydrogeosphere. They develop naturally through the physics of the simulation. So we'll explore this key strength of hydrogeosphere in today's webinar, which is delivered by my colleague, Dr. Mike Callahan. Mike is a senior applications engineer at Aquanty with over 25 years of experience in the geoenvironmental sector, including over 20 years of numerical modeling experience, ranging from the soil column scale to large river basin scale, spanning diverse applications such as river sedimentation modeling, salt and pesticide leaching to environmental receptors, hydrologic risk assessment for agriculture, regulatory permitting for mine development, and more recently, integrated hydrologic modeling for groundwater supply. Mike, thanks in advance for taking the time yet again to deliver another webinar for us. Take it away.
Thank you, Braden. Thanks for that introduction. Just before I start, I'm going to turn off my camera for the actual presentation, just to reduce distractions, and then I'll turn it on again at the end of the presentation for the Q&A period. Okay. All right. So before I start, I'd like to thank some of my collaborators who have provided many of the examples I'll be using in my presentation. There are quite a few towards the latter portion of the presentation, and obviously not everyone's listed, but I've tried to capture kind of the main contributors there, and so my apologies for anybody who's missed. As Braden sort of described and gave a really good introduction there. The title of my webinar is Flee from Parsimony, Escaping the Boundary Condition Paradox in Groundwater Modeling. And as I'll explain through the presentation, the sort of ulterior motive for the webinar is to, somewhat convince you to consider working more with integrated surface-subsurface hydrologic models. All right. So what is meant by parsimony? So the title of the presentation is, is somewhat dramatic. We've got words like fleeing and escaping in there, and it's, it's really designed to capture your attention for something that, we're quite passionate about here at Aquanty. And it also gives us the opportunity to highlight what we see as the sort of major conceptual difference between traditional groundwater modeling and integrated surface-subsurface modeling. And so you might find it informative and useful, right? So what is parsimony? So parsimony in a modeling context, particularly in hydrology, refers to the principle of preferring simpler models that adequately explain the data over more complex ones. So in our sort of context here today, we're talking about like sort of looking at kind of a simpler setup for kind of like the physics of, say, a groundwater model versus the more complex integrated hydrology in a model such as HGS. And, it's kind of a presentation where I want it to be kind of philosophical. It's not like we're here to tell people when they should use an integrated surface water groundwater model. It's more along the lines of that I think pretty much all modelers, all groundwater modelers and other surface water modelers, etc., reach a point in a certain project or in their career where they run up against certain frustrations, and so I'll kind of talk to that as well. So by the end of the presentation, I hope to have sort of convinced at least some of you that sort of a simpler and more accurate conceptual model can result from a more complex numerical model. And the sort of turn of phrase that we use internally here is sort of just rain on your model. So as the title of the presentation suggests, so I'll be focusing on kind of the upper boundary condition of groundwater or integrated models. So, let's kind of take a look a little bit deeper into, what is meant by recharge in terms of a modeling context. If we want to incorporate recharge into a model, we sort of need to first know what we're trying to capture. So if anybody's interested in kind of deeper reading on this topic, I can recommend this paper that's published in WRR in 2023, includes one of Aquanty's founders, Renee Therrien, as an author, and as well Philip Brunner and Peter Cook, who sort of wrote the textbook on quantifying recharge. So, the good place to start is with the definition, and it's always a little bit eye-opening when there's complexity even within the definition of recharge. So for such essentially such a simple concept as the water entering the top of a numerical model, in terms of the sort of real world definition, there's quite a multitude of definitions out there. So from that paper, so 3 of them are: recharge is the downward flow of water reaching the water table, adding to groundwater storage. Could also be the entry of water into the saturated zone. So that definition sort of inherently includes the capillary fringe. The next definition, the rise of water table minus groundwater discharge, so sort of the net result of recharge. And then another more sort of soil science kind of based approach is that all water that passes the root zone. So basically here we're looking at recharge in terms of unconfined aquifers. But even for something that we as modelers spend so much time kind of thinking about and perhaps debating, recharge itself is only of indirect interest to water resources management. Things that like on an individual project, we might want to know recharge in terms of it being the source of water for resupplying a pumping well field. We might want to know, is the development sustainable in terms of sort of space flow for streams, or is it, is a contaminant going to migrate a certain distance? So even though we spend so much time thinking about it, it's really only a secondary thing to our the actual question at hand usually. Okay, so this brings us to kind of the recharge condition paradox, and Braden gave a really good introduction to it. And here I'm just going to sort of keep it fairly simple in that, recharge and discharge are of great interest as outputs from a model, but often they're used as model inputs, right? And it can be calibrated. So, if we know how much water we have coming into the system, then it would be great to actually have strictly a model output rather than the model input, as is often the case. So, there's a couple caveats there. Technically, recharge can be calculated from a defined water table position, but it really requires almost a perfectly known hydraulic conductivity field, which is generally not the case. The other common methods used to specify recharge in a model, would be to have recharge rates calibrated along with hydraulic conductivity, and that can suffer from inherent non-uniqueness. So the figure on the right is just here to kind of illustrate, it's an example of a recharge map calculated using the water table position method with, all the caveats kind of being satisfied. And its main purpose here is to show the high variability of the calculated recharge field. It would be very difficult to capture something like that using a recharge area approach to break it out and capture that level of spatial variability. So if we come back to the paradox, if we're interested in sustainable water supply or sustainable hydrologic landscape, and we force a model with a specified or even calibrated quantities, we're telling the model where recharge is going to occur and likely when. It would be sort of liberating instead for the model to tell us where the water wants to go instead of the other way around. So I have, some suggestions as to when you might want to try to kind of escape the paradox. And I think this is a point where most modelers have reached at some point. A good example is when you have too many recharge areas in your model and they may not be supported by topographic or material differences. That's a very common one that we hear from sort of our clients and customers. You may also be having trouble calibrating your model to observed groundwater heads, or you may not even be able to get your model to converge. That's often been an application for hydrogeosphere, is to sort of reconfigure an existing model and actually get it to converge. And lastly, you may be trying to model an unknown system where you just don't have groundwater level observations to calibrate to. So this can include a lot of sort of hypothetical modeling, so climate projections, land cover changes, or even sort of new landscape designs, such as in mining reclamation. So the solution I'm presenting here is to kind of rethink the recharge-based conceptual model and move to a rainfall and evapotranspiration-based integrated surface subsurface model like hydrogeosphere. So, what do we mean by a fully integrated hydrologic model? So it's a model that simulates the entire terrestrial water cycle. It's forced by rainfall and evapotranspiration. Depending on the state of the system, excess water can either infiltrate into the ground or it can run off. So then this can have a direct impact on things like soil water storage, water table position, surface water, groundwater exchange in both directions. And it's sort of nicely illustrated with the animation on the right, where we see sort of infiltrating water, the resultant rise in the water table, and rise in surface water. So the basic takeaway from this is that the effects of rainfall on both groundwater and surface water are included simultaneously. So just in terms of the long-term development of hydrologic models, both surface and subsurface, how did we get to the position of simulating both surface water and groundwater together in the same model? So the evolution of the modeling sort of starts on the left-hand side of this figure, where we have standalone surface water models and standalone groundwater models with a few examples. For groundwater models, the classic examples would be mod flow and feed flow. And so those two models, in typical applications, they might be run separately with the results of one model, such as a surface water model, being used to inform the groundwater model. So perhaps recharge is being calculated using some sort of a surface water model, and then that is being applied as a boundary condition to the groundwater model. So in the middle panel, sort of in the middle of that transition with what we call loosely coupled models. So they're models that include separate surface water and groundwater modules, and the passage of information like fluxes between the two models occurs at a certain time in the solution. So good examples of loosely coupled models would be like Mike Shee and GS Flow. So fully integrated models solve for both the surface water and groundwater flow at the same time in the same numerical matrix. So whatever's happening in the groundwater is directly connected to what's happening in the surface water. So two good examples for fully integrated models are hydrogeosphere and Parflow, with sort of our background with hydrogeosphere is sort of the sole presence in commercial applications. So in the previous slide, I introduced loosely coupled and fully integrated models. We also often use the term tightly coupled in place of fully integrated. And what I wanted to point out here in this slide is you know, if anyone's interested in kind of additional information on what the sort of implications of fully and loosely coupled models are, you could check out this 2017 paper. The benchmarking paper includes some examples of both models, and it was, you know, Aquanty and the other model developers participated in putting this paper together. So the example results on the right are for a small, sort of just a demonstration model. It's called the V catchment model, where rain is applied to the top surface, and then on the right are the sort of responses, the hydrologic responses, showing saturated and unsaturated storage behavior in the top two panels, and ponding and surface water discharge in the bottom two panels. So HGS on these plots is in black, so it's the kind of the example that we'd be using for a tightly coupled model, and then we have a loosely coupled model in green for comparison there. And basically the sort of effect of the loose coupling can lead to sort of numerical instability, particularly noticeable in the ponding volumes and a little bit in the surface water discharge. So sort of just keep in mind that this is for a small demonstration model and not a large realistic model, but basically the fully integration has a tendency for better stability compared to loose coupling. Okay, so the demonstration model was sort of a rain-only model, that one that we looked at in the previous slide. So here on the left, we have kind of the conceptual model for hydrogeosphere with precipitation as an input, as well as potential evapotranspiration. So potential evapotranspiration being the evapotranspiration that would occur for a reasonably wet ground surface. And what the sort of the process of calculating actual transpiration in HGS accounts for water limited conditions for both plants and soil, and as well as evaporation from surface water. So it's sort of one of the great strengths in determining like the water availability for recharge is the calculation of actual evapotranspiration. So in terms of calibrating an HGS model, typically, I mean, we would be using traditional measures like groundwater levels, but also soil moisture and perhaps things like observed evapotranspiration or sorry, I wanted to mention surface water, either flows or levels. And, you know, we don't directly tell the model where the streams and rivers are going to form as boundary conditions, in that the integrated surface-subsurface model allows water to flow naturally. So those water bodies form naturally on their own. So to build on that last point, in an integrated surface water-groundwater model, the recharge and discharge areas are not defined upfront. So this is what I referred to at the beginning of the presentation, that the conceptual model is generally simpler for an integrated hydrologic model than for a groundwater-only model. This is how sort of integrated hydrologic modeling escapes the paradox of specifying recharge and discharge boundary conditions. So on the left, I have an example from literature of sort of boundary conditions set up for a mod flow model. Very typical sort of recharge areas are shown in the leftmost figure, and in the middle it's the river boundary conditions. You know, it's of note that the authors specifically mentioned that it would be prohibitive to include all river boundary conditions, like all discharge areas in the model. In the right-hand panel, we have an animation of infiltration and discharge areas in HGS, just sort of an example where discharge areas are in red and infiltration areas are in blue. So, you know, what's kind of useful to take away from this is that they're not defined a priori, like the recharge areas and discharge areas are not input into the model. They develop naturally from the model output. So this has a lot of power for kind of prediction of things like, say, wetland occurrence and the presence of rivers, lakes, direct and direct sort of implications on flow. Okay, so now I'm going to transition sort of away from kind of the recharge specific kind of discussion and focus a little bit more on sample applications to kind of address some of the interest we're seeing from our clients and customers in the modeling field for use of integrated surface subsurface models. So this is a fairly comprehensive list. I'll go through it, but then I'll focus specifically with some examples just after this slide. So climate change impact assessment on water resources, that's probably got to be the number one interest that we get with applying hydrogeosphere models. It seems to be almost ubiquitously an add-on to an HGS project. Cumulative effects is also quite common. So looking at the combined effect on both groundwater and surface water, both from a quantity and a quality perspective. Regional and national water resources studies, we're seeing a lot of application there. Water quality for multiple pathways, again, surface water, groundwater, perhaps tile drainage. So in the agricultural field, traditional groundwater surface water interaction is obviously still quite a common application for integrated surface subsurface models. Fairly new is forecasting. So we're seeing a lot of HGS models being turned into forecast platforms, both from, say, forecasting groundwater levels to surface water availability or soil moisture, and even flood forecasting. Cross-validation of large-scale water resources using remote sensing. I'll show an example a little bit later on of the GRACE satellite results for an HGS model. And then ecosystem goods and services, like things like simulation of the presence of wetlands, persistence, change over time, especially with under climate projections. Okay, so the first application I'm going to show is meant to highlight the sort of very rapid spatial variability of groundwater recharge. Specifically, this is during a flooding event. This flood event occurred in High River, Alberta, in Canada. One of the interests from the municipality was the potential for municipal well contamination from floodwaters. So their pumping field was actually installed within the floodplain, and it's very high hydraulic conductivity sands and gravels. So in the upper left, you can see an air photo of the flood inundation from the June 2013 flood event. So basically the entire center of town was inundated, including the well field. In the lower left corner, I've got a small key there showing. It's basically going to show it's the key to the colors for the animation that I'll show. So incoming surface water flood wave is in red, and the initial sort of groundwater fraction is in blue. So anything that was groundwater is in blue, and anything that's coming in as recharge from the surface is going to be tagged in red. So I'm just going to start this animation here, and this spans about 12 hours of flood wave passage at two depths. These are both in the subsurface. So one is the ground surface itself, and the next slice down that I'm showing here is at 1 meter depth. And so the initial water table depth was about 2 meters in this case. So at 1 meter depth, the proportion of surface water recharging the water table is much lower than at surface. I think that makes sense because it's there's all the sort of antecedent water. It was quite wet ahead of this flood event. So the point I want to get here is that distribution of infiltrating water changes with depth, and the spatial distribution is very complex and rapidly varying. So this would be something that would be very hard to reproduce using kind of a traditional recharge boundary condition in a groundwater only model. Very high spatial variability and very high temporal variability. And I move on to the next example. So this is kind of more of a classic example of calculating groundwater contribution to stream flow. This application is sort of most similar to use of a traditional groundwater model. This model was used to calculate the groundwater contribution to the Athabasca River in northern Alberta, Canada, for the whole basin. But instead of calibrating a groundwater only model to base flow, the integrated hydrologic model can be calibrated to total stream flow. And that's actually quite an advantage because stream flow measurements are can be considered to be known fairly accurately, whereas base flow is a concept with multiple definitions and even more methods to calculate it. So that tends to add to the complexity of the kind of interpretation, whereas just using straight stream flow is actually essentially a simpler approach. So again, I mentioned in the previous slides, one of the most requested applications for HCS models or for climate change impact analysis, either for groundwater or surface water or both. This is an example of modeled climate change impacts for the Grand River watershed in southern Ontario. What makes HGS well suited to climate change impact analysis is that it's fed with precipitation and potential evapotranspiration, and both of those are typical outputs from climate models. So there's essentially a fairly direct mapping of inputs from the climate projections into an integrated surface-subsurface model. So the model's typically calibrated to historic climate conditions, and then the climate projections can be directly added after that. So because recharge is highly nonlinear and it's a product of climate inputs and site-specific characteristics like soils, vegetation, direct calculation of climate change impacts on recharge is highly uncertain. And since the physics behind HGS remains the same, whether we're talking about in the past or in the future, the projected recharge outputs from HGS are physically based and therefore more accurate. So here we have a mining application where essentially the unknown here is that the land surface is essentially changing with time. So we might have historic data to calibrate a model, but we don't have sort of future data. So we're getting more and more kind of requests, both from, say, client side and regulatory side, is for continuous simulations. So as opposed to just the snapshot approach where one might simulate the pre-disturbance stage, the mining stage, and then the reclamation stage, is to have all three of those stages in one model. And so it's what we're being asked to provide is basically, answering questions that are related to the timing of the different mining stages. And so that's very hard to do in a snapshot approach, but it's relatively straightforward if you've got a continuous simulation. So aiding in this this analysis is to simulate time varying topography in HGS, and it's shown on the right hand side there in that animation is the resulting effect on water table position, and then other outputs such as we could look at recharge or capture zones of water control measures, etc. So the next application is kind of conjunctive use of groundwater and surface water from one domain and then using it in another domain, so such as surface water being extracted and then injected into groundwater, for example. So just like in managed aquifer recharge, on the cross section on the right, water is being extracted from the surface water body and being ejected into an aquifer. So, by definition, the conjunctive surface water groundwater use motivates simultaneous simulation of both extractions and additions, either through injection wells or surface applications such as ponding or irrigation. So this sort of water movement is it's easy to implement in an integrated model and then observe the interactive effects between the different water sources. Sorry, I believe my last slide didn't advance, but I'm going to jump ahead to the remote sensing application. So the next example is the application of large scale water resources remote sensing, so such as the GRACE satellite. So what's kind of unique about integrated hydrologic modeling is that it captures all components of that terrestrial water cycle. So it's got the surface water, groundwater, and snow components. So this example here shown on the right is from Southern Ontario here in Canada. And the HDS simulated multi are shown on the top plot, and then the direct sort of comparison of HDS results to the GRACE satellite anomaly is shown on the bottom plot. And while this isn't, it's not specific to considering recharge, it does demonstrate the sort of that how the entire water balance is closed and included within an integrated surface subsurface model. So it really takes a lot of the uncertainty about those interactions out of play. So I mentioned forecasting in the sort of the summary slide before we got into the applications, and it's almost similar to the climate projection scenario, where it's fairly readily available to get weather forecasting information in the form of rainfall and potential evapotranspiration. It can then be used to directly force the HDS model. Where we're seeing applications for this are in sort of short-term, week to 2 week sort of forecasts, as well as seasonal forecasts that might be on the order of a few months. And a perfect example is we've had seen interest just in the last little while relative to the upcoming Super El Nino. Is it going to have what are the effects going to be, say, on aquifer recharge for a specific area? So just a second here. I'm just having a slide. There we go. Slide mix-up on my end. So to sort of summarize, change in one component of the water cycle directly influences the other components in a physically realistic way, avoiding sort of empirical relationships. That full integration kind of improves model stability and therefore accuracy, right, relative to loosely coupled models. With all flow being accounted for, precipitation, ponding, evaporation, infiltration, transpiration, there's essentially no missing water in the water balance, so the water balance can be closed. So in conclusion, what the value proposition is for using an integrated hydrologic model is really that raining on a model and letting the water flow where the physics dictates is conceptually easier in deciding where and when recharge and discharge will occur. So HGS itself is particularly applicable to shallow groundwater flow processes, such as classic groundwater surface water interaction problems. But overall, a more integrated approach helps model the users to make better informed decisions that are now commonly required components of groundwater and surface water projects. And with that, I'll turn on my camera, take some questions, and I'll turn it back to you, Braden.
Thanks a lot, Mike. That was a very informative presentation. Yeah, we have plenty of time now for questions, and so I'd like to just open up the floor. If you have a question, feel free to type it in the chat or the Q&A. You can also raise your hand, and I'd be happy to unmute you, and you can just speak your question out loud. A question from Clarissa. How do you deal with time stepping?
Yes, that's a good question. So time stepping in HGS is it's completely implicit. So what that means is we basically have a whole set of parameters in the solver that sort of controls how that time stepping occurs. In terms of time step itself input, we input a maximum time step, and then a series of parameters that adjust the time step relative to essentially how hard the solver is working at any given time. So, for example, if a wetting event comes through, like say a precipitation event, the time step is cut automatically by the model, so it reduces the time step to deal with that sort of incoming hydrologic shock. And then as the shock dissipates, the time step opens up, potentially up to its maximum.
Should also potentially note that time stepping is always going to be constrained by target times within hydrogeosphere. And so if you have daily transient boundary condition forcing data, then your time steps by extension would be limited to a maximum of potentially 1 day in length. But if you have less high resolution transient forcing data, perhaps monthly average precipitation, for example, then the time steps will have a little bit of room to grow. But as Mike said, ultimately it depends on how the solver is operating, and the user has full control over a number of different time stepping control targets. And so if hydraulic heads start to change rapidly, then the time step will automatically shrink, and if things steady out, the time step should automatically start to grow. A follow-up question here from Clarissa. And the groundwater and surface water are all solved in every time step? And the answer to that is yes. Mike, if you have any other comments.
Simply put, that's correct, yeah.
Thank you for the questions, Clarissa. We are happy to take any other questions anybody might have. More questions from Clarissa. Excellent. What kind of grid resolution do you need in the vadose zone?
So I think you're talking about vertical grid resolution. It does depend on the scale of the model, the size of the model, essentially. So I'll give you a few examples. I work from soil column scale all the way up to watershed scale and even river basin scale. So when I'm doing, say, contaminant transport at in a column scale, I would be using something on the order of 10 millimeters mesh resolution, vertical mesh resolution. Whereas, when we go to the larger scale, typically we have our mesh or our mesh sheets telescopically sort of spaced closer to the top of a model. Typically something around 5 to 10 centimeters for your first sheet, maybe 15 to 20, 30 to 50, 1 meter below that. So it really does depend on the kind of the scale of the model application, but yeah, it's completely flexible.
As with any model, you're kind of constrained by computational limitations, right? Ideally, we could have a layer every centimeter, but it depends really on the overall spatial scale of the model and the grid resolution, both laterally as well. Another question has come in. Can we get field or farm level drainage or runoff?
Oh, for sure. So again, it depends on how you build your model, but if you are sort of building in features on the scale of a farm field, then yes, I mean, you would get your typical outputs that you get from an HDS model in terms of fluxes are going to be your runoff, infiltration, any fluxes in the subsurface, so flux through, say, below the rooting depth or flux at the top of an aquifer, that's completely flexible. And then you can incorporate, we have a specific tile drainage domain where we can build in linear tile drains into a model, but we often also model tile drainage with just sort of what we call a simple drain boundary condition, which is a third type boundary condition. So that's quite a common output from an HGS model.
And just to kind of illustrate this a little bit, I'm just going to share my screen very briefly. Sure. We have this little clip on our YouTube channel which just shows what we call the prairie pothole simulation. So here we have potholes that are about 20 meters across, but you can imagine with the underlying mesh here would be probably quite refined in the grand scheme of things in terms of what we often do with hydrogeosphere working at the watershed scale. But every model, of course, is built to purpose, right? So if you're interested in field or farm level drainage or runoff, you would just need to fully parameterize that to the best of your abilities and, build a model to basically right scale the model. So we have some more questions. So from Aspen, I believe I remember the answer to this, but can you confirm if hydrogeosphere can handle time-varying hydraulic properties, for example, unsaturated, saturated hydraulic properties changing due to consolidation? And I can briefly answer that, and the answer is yes. In hydrogeosphere, we support time-varying properties in many model domains. Time-varying hydraulic conductivity is 100% possible. It's often used to represent, for example, soil consolidation, but also pore water freezing and thawing. In the surface domain, we can also apply time-varying Manning's friction coefficients to represent perhaps winter conditions where liquid water is not going to flow because it's not liquid. There's a number of other properties and that can also change over time in hydrogeosphere, for sure. A follow-up question from Clarissa, further to the questions on time stepping. So it seems like your computational runtimes would be quite a bit longer than a groundwater-only model. Is that right? Any rule of thumb on how much longer? The answer to that question is going to depend on which groundwater model you're comparing hydrogeosphere to. If we wanted to compare hydrogeosphere to ModFlow, we can say unequivocally that the hydrogeosphere model runtimes would be significantly longer. And that's just by virtue, not necessarily of the time-stepping behavior, but the nonlinear nature of the underlying governing equations of flow. So if we were to look at a different groundwater-only model, such as FeeFlow, which handles three-dimensional variably saturated flow just like hydrogeosphere, the model runtimes could be comparable. Depends, of course, on a number of different factors, the overall conceptual model, the scale of the model, et cetera, et cetera. But it really it's not a matter of the integrated nature, I think, of the model so much as it is the fundamental nature of the underlying governing equations. Any further thoughts on that, Mike?
Sure. Yeah, it's sort of specific to the rule of thumb. Yes, model runtime is always a consideration in, well, I mean, in almost all numerical modeling, like complex numerical modeling, but especially in hydrogeosphere modeling. And we'll often work backwards from, what is a reasonable model runtime? For smaller models, small like watershed sort of size models, you might be looking at hours. In terms of very large regional models, you would be looking at days. But what we do is we often target that time. So we'll build, usually what we do is for a very complex model, we'll build sort of a simpler version and basically test the runtime. Add in model refinement if the time allows. So it's quite a flexible process. So there's no sort of magic number about, the model runtime is going to be X. It's more that we work towards meeting a reasonable model runtime.
Another thing that should potentially be mentioned is beyond model runtime, we also need to, in order to effectively use hydrogeosphere, you often need to implement a little bit of rigor in terms of your overall project management approach. So as Mike said, we'll start with a coarse resolution mesh, but a lot of the lessons that you learn from that coarse resolution mesh can be easily applied to a much higher resolution simulation for that same overall conceptual model and overall location at a higher resolution. So in hydrogeosphere, we support a number of what we call regional model commands that allow you to map certain information from typically a larger in scale model onto a smaller local model. But in fact, the quote unquote local and regional models can have the exact same footprint, just with different mesh resolutions. So you can go quite far with a coarse resolution model mesh in hydrogeosphere and then swap in a high resolution mesh sort of later into the project, so you can have basically try to move as far down the project timeline as you can with the coarse resolution mesh before swapping in something with higher resolution. We have a question here about calibration, which I'll leave entirely to you there, Mike, but I wonder how you approach calibrating your models. I understand that the physics within HGS represents a sort of quote-unquote reality, but many measurement uncertainties and soil responses require calibration to some extent. Conceptual models tend to have much smaller runtime, so I was wondering if you could comment on this.
Yes, I mean, conceptual models obviously do have shorter run times, but then you are kind of limited by the realism of those fitting parameters, right? So, in terms of model calibration, the approach to calibrating a hydrogeosphere model is very, very similar to calibrating a traditional groundwater model. In fact, we tend to prefer similar software for automatic model calibration. And, what you do in that process is you set up your parameter sets to have a reasonable physical range, right? A priori generally what, say, certain material properties are for, say, a sand or a clay or, a limestone. And then you're calibrating to within a reasonable parameter range. The other advantage of calibrating an integrated surface-subsurface model is you're not limited to just observations from, say, groundwater or surface water. We tend to incorporate both. So very sort of classic HGS model calibration, you will have observed groundwater levels, observed stream flow, temporally varying stream flow, as well as sometimes we'll have actual evapotranspiration measurements or soil moisture measurements, and sort of having that kind of multitude of different observations in your objective function really overall improves confidence in model calibration.
Thanks, Mike. We should probably do a webinar on model calibration specifically. I think that would definitely be of interest. There was a follow-up question, which I think you kind of touched on here, but to follow up on this, is there an active community building API-like tools for programmatic HGS model setup, execution, and post-processing so as to facilitate calibration and uncertainty analysis or optimization via external tools like PEST?
Yeah, I mean, Braden, I can sort of get your input on this. Like our current sort of most active community is probably the LinkedIn community, I would say. We used to have Google Plus community, but that when Google discontinued Google Plus, that sort of went away. In terms of published examples and published tutorials, there is actually a very good HGS PEST tutorial for pilot points that I think, Braden, do we have that one in our sort of quiver of examples for training, or is that one strictly like hosted like as a publication elsewhere?
No, we tend to try and put as much of our material out there for consumption at any time by anyone. So we do have a tutorial on PEST. To answer your question directly, there is no community building API-like tools for programmatic HGS model setup and execution necessarily. There is a LinkedIn community, user community, where people are actively asking questions, posting HGS research, et cetera, et cetera. And definitely a lot of our user base has developed a number of tools for, as he put it, programmatic HGS model setup, execution, and post-processing. We're also available to help you with that, developing batch processing scripts for model calibration is quite simple, something that we've done regularly ourselves, and I know that a lot of our user community does. But there isn't necessarily a let's call it a GitHub type user community developing and publishing scripts and tools for programmatic HGS setup and execution, as you put it. Scrolling back up, I think I missed one question. And so Yaming says, thanks, Mike and Braden. My question, yes, the HGS system solves the surface water-groundwater interactions implicitly to calculate the recharge from the surface water system into the groundwater system. Still, you need to assign recharge on the land surface of the surface water system, right? How did you do this in the examples you presented? And I can probably handle that one. We don't actually apply a recharge boundary condition. We simply apply precipitation data. Precipitation data is directly observable, measurable, widely available. So we completely sidestep the question of what groundwater recharge is by simply applying, as Mike said, we just rain on the model, apply precipitation directly, and the physics of your simulation, the soil parameters and current soil moisture, et cetera, will dictate that runoff versus infiltration. We've got lots of questions today. It's really good to see. A follow-up question on time-varying properties from freeze-thaw. Can hydrogeosphere simulate the freeze-thaw of pore water considering atmospheric temperature, or would that be a user-specified input? Great question. Hydrogeosphere does, in fact, have a number of built-in winter processes and features, such as dynamic pore water freezing and thawing, which is based on a user-specified schedule of atmospheric temperatures, as well as a number of other factors like the thermal conductivity of soil and things like this. However, it really depends on the scale of the model whether or not that would be actually applied, at least in our experience. At Aquanty, we do tend to work on larger watershed scale models, and we've found that it can potentially be more efficient, numerically efficient, to just calculate some of these things offline and apply them as a user-specified schedule of, let's say, hydraulic conductivities. The same would apply for other processes like snowmelt and accumulation. You can rely on the native snowmelt and snow accumulation boundary condition in hydrogeosphere, we typically do on an operational basis. We run a real-time hydrologic forecasting platform, hydroclimate site, for example. We will, rather than using that native snowmelt and accumulation boundary condition, we'll simply calculate snow water equivalents and the liquid water flux on a day-to-day basis and apply that as a liquid water flux to the model. Another follow-up question on the question or the discussion on hydrogeosphere model runtime. Is it feasible to run a watershed scale surface water groundwater model with, say, 5 million nodes or elements using a laptop or a desktop computer today? I used to run hydrogeosphere using the WestGrid supercomputers 20 years ago. I would say this is hard to say as usual because there's a number of different factors involved in model runtime. Like, for example, if you had a 5 million node simulation and you wanted to run it at watershed scale, the question, a big question becomes, are you trying to run this using daily transient forcing data, or are we looking at long-term climate change simulations? Generally, though, we've made incredible advances in terms of the computational efficiency of hydrogeosphere, especially compared to 20 years ago. We now can parallelize hydrogeosphere locally. Everything that we do at Aquanty, for the most part, is done using off-the-shelf computers. We buy boxes from some computer supplier. We're not, we don't operate a supercomputer or anything like that. In our office, we're not really relying too much on these types of HPC environments. So with the right project workflow, working in a staged approach, which, we've got other webinars that talk about this, optimizing models and optimizing them for convergence and increased or decreased runtime, I should say. With a good project workflow, good discipline, and an eye for efficiencies, you could probably run a 5 million node model on a desktop computer. How long the total model runtime would be, impossible to say, really. Any other comments, Mike?
No, that's yeah, it's pretty good. It's yeah, what you'd call sort of off-the-shelf computing power has come a long way in the last 20 years. And generally what we're sort of, what we're buying for our internal processing is sort of high-end kind of gaming PCs. You don't need anything fancy in terms of graphics cards, for example, so you can usually save a little bit money there and put the money into kind of the fastest CPUs available. And that's been working well for us for well over 10 years. So yeah.
Get yourself the best processor you can with as many cores as possible. I see that somebody posted the PEST tutorial. Thank you very much for that. This has been a great series of questions. I'm not seeing any other questions coming in, so I guess at that I'll thank everyone for the many questions, a good discussion. I'll thank you again, Mike, as well, for delivering the webinar. Everyone, keep an eye on your inboxes for a follow-up email. I'll be sure to send the recording around, and again, hope you'll share it with your networks. If you have any follow-up questions for us here at Aquanty, don't hesitate to reach out. Thanks, everyone.
Thank you.